Imagine standing inside a chamber so empty that a single molecule wandering through the darkness becomes an event worth measuring. No wind, no sound, no pressure, almost no matter at all. This chamber is larger than a house, yet compared to the manufactured vacuum inside it, the vacuum of outer space is actually crowded with molecules. Civilization's most sophisticated technologies depend on removing everything rather than adding something new. These artificial environments manufacture our computer chips, test our spacecraft, and support the extreme physics inside particle accelerators and fusion reactors. Progress at the limits of engineering is defined by subtraction rather than creation. For thousands of years, philosophers believed nature hated emptiness. This idea, known as horror vacui, held that nature abhorred a vacuum, meaning every attempt to create empty space would fail as surrounding matter rushed in. In the 17th century, miners hit a wall. As mines became deeper, groundwater flooded tunnels faster than workers could remove it. Existing suction pumps consistently failed to pull water upward past a certain height. The bottleneck appeared mechanical, but the cause was atmospheric. Engineers discovered that suction wasn't pulling the water, atmospheric pressure was pushing it. Invisible air possessed physical weight and force. If pressure existed, it could be removed. Researchers built primitive vacuum pumps and watched as candles extinguished, animals struggled to breathe, and sound disappeared. Redefining the problem from a mechanical failure to an atmospheric property made manufactured emptiness possible. Removing most air is relatively easy. Removing nearly all of it is extraordinarily difficult. The closer engineers approach emptiness, the harder physics fights back. Matter clings to surfaces. Molecules hide inside microscopic cracks. Metals absorb gases, and even solid materials continuously release trapped atoms. The first practical electronic amplifiers required a controlled vacuum to function. By removing air, engineers could precisely control the movement of electrons. These controlled voids birthed massive industries. Radio, television, radar, and early computing all depended on vacuum environments. In modern semiconductor manufacturing, the scale of the problem shrank drastically. At nanometer scales, a single stray oxygen molecule or a trace impurity becomes a catastrophic contaminant. Removing atmospheric interference was the foundational step required to manipulate matter at the microscopic scale. Creating a vacuum is not a single action, but a hierarchy of challenges requiring escalating technology. First, mechanical pumps remove the bulk air. They clear out the major volume of gas, but eventually hit a wall against finer, faster-moving molecules. To handle these remaining gases, turbomolecular pumps use fast-spinning, angled blades to physically bat away lighter molecules. For surface contamination, cryogenic pumps create ultra-cold surfaces that literally freeze rogue molecules in place on contact. Finally, ion pumps are used to magnetically trap the final charged particles escaping from the chamber walls themselves. Every stage of improvement only exposes a smaller, more resilient source of contamination. The engineering of emptiness is a relentless war against progressively smaller states of reality. Trillions of dollars of modern industry now operate inside these artificial voids. In particle physics, proton collisions at the Large Hadron Collider would be ruined by stray gas molecules. Protons travel through a beam pipe where the vacuum approaches the conditions found in deep space. Experimental fusion reactors face a similar requirement. To survive, plasmas hotter than the sun must be totally isolated from ordinary air inside evacuated chambers. Testing space on Earth creates a logistical problem. To ensure a satellite survives the trip, engineers use colossal thermal vacuum chambers that reproduce the extreme conditions of the cosmos. These structures remove nearly all air while recreating extreme temperature shifts to validate multi-million-dollar satellites before launch. Our ability to explore the subatomic world and the literal cosmos depends on our ability to perfectly simulate nothingness on Earth. Despite 4 centuries of engineering progress, achieving an absolute vacuum remains physically impossible. Quantum mechanics reveals that empty space is not empty at all. Instead, it possesses an inherent buzzing structure. Particles spontaneously appear and disappear through quantum fluctuations, ensuring that perfect emptiness can never be reached. Mastering nothingness has become an infinite pursuit without a finish line. The closer we move toward perfect emptiness, the more we discover there is always something left to remove.